All right, welcome back. This is going to be another one of the sample section 3 walkthrough videos where I go through all of the work solutions to a bunch of questions that I've written up in practice for the September sitting now. You might be watching this, I don't know, maybe into the future then, and then people might still be watching these in a while. I'm obviously not sitting in anymore. My March 2022 sitting was the last one. I'm now in the application process, but for those still studying, I'm going to keep making resources, and that includes a whole bunch of free questions which are available on my resources page that's linked below. And this will be set number 13. So now this is another 9 questions. It seems to be 9 every time. So this should now push us to 120 questions that are now available on there. And then the goal will be to hopefully also be able to create some like full length practice exams and that kind of thing. But I've got to get the balance right and stuff. So it takes a little bit more practice. At the moment though, I'm building up a really good bank of questions that are hopefully relatively reflective of the real thing. Anyway, we'll go through these ones here. So these are a little bit more maths focused. I know this is a real kind of weak point for a lot of candidates and a lot of people are really unsure about it. The other thing is as well that yes, there are the 3 disciplines of biology, chemistry, and physics, although maths is a skill that kind of blends itself into all 3 of those disciplines, really heavy actually into the biology stuff because a lot of that is very data driven. So realistically, the questions that I've written today seem like they kind of fall under the categories of biology and physics. However, you don't actually need to know any knowledge to answer them. There's no specific science knowledge being applied. It is literally just about mathematical reasoning all the way through. And I'll hopefully point that out as we go through the questions as well. Okay, so let's start here. I'll just make sure that's all locked. And I'll go through the reading. The links are there as well if you wanted to read the original papers. I'm trying to also do a video where I kind of explain how I actually build these questions, but the basics of it are that I basically usually just try to find raw original research data, and then I look for data that basically could be turned into a question set, and then I build a question around that, trying to apply specific skills. And I'm usually like pinpointing 1 or 2 key conclusions that can be taken from the information presented. And sometimes that also includes chopping up and changing the way that it's presented to simplify it so that it kind of fits into a GAMSAT context. So let's jump into this one. So we've got development of arbuscular mycorrhizal or AM fungal colonization. So whenever we see AM now, we know we're just talking about that particular fungus. Colonization of roots and the surrounding soil is the central process of mycorrhizal symbiosis, important for ecosystem functioning and commercial inoculum applications. Most of that, even to me, does not make any sense whatsoever. I understand that there's fungus, I understand there's some kind of infection or something, no, that's later on, that it's a central process to symbiosis, so the kind of working together of 2 different organisms. I remember mycorrhizae and things like that from my undergrad, but you don't need to know anything from that at all to be able to answer this question. So a study was conducted into the development of AM root colonization of this particular one. Whenever I see the Latin genus and species, I always pay pretty close attention to that because that might be the kind of handle that they're going to link through the rest of the question. Using a 2-stage experimental setup, the aim was to measure the AM colonization rate of a root system connecting to an already established AM soil mycelium. In the first stage, donor plants were grown in 90 boxes filled with a 10-45-45 split weight for weight for weight, which is what the W means. Mixture of a moderately low P soil or phosphorus soil. For soil characteristics, see table 3, and we can see that down here. So this represents our 10%, of course, and then also coarse sand and zeolite as well, which I have no idea what the hell zeolite is. Half of the boxes received a soil inoculum containing viable propagules, I guess, of the AM fungus Rhizophagus irregularis BG158. A lot of that just goes right over my head. I'm just going to know, okay, that is in there. And then control group has no viable propagules added to the box. So this is the non-mycorrhizal control group. Makes a lot of sense. You've got the IV in there and not in the other. So plant growth, shoot and root dry weight was determined at 4 harvest dates, 36 blah blah days after adding the inoculum. Okay. So if I was making notes on that, I'd probably try to draw this one out. So I just draw 2 boxes and then I would just write like a reminder 10-45-45. And this is 10-45-45. And then the difference is this one has the inoculum, whatever that actually means. And that is it had that AM something or other. What did it say? I forgot my own question. the propagules. So I'm going to just put down all those keywords so I know what I'm looking for when I'm actually going through the questions, and I'll know what's going to trigger my memory of which group I'm in. And this is obviously going to then be the control without that there. All right, so then we've got table 3 as well. So we've got the characteristics of it. It splits it up. It gives us percentages of all the different components. And then I usually don't spend too much time on the actual tables and that kind of thing because it's very disjointed information. Then depending on the density of the propagules in the soil, root segments can become infected with the fungus with a certain probability P. So now we're getting into some maths and equations here. To obtain independence from the spatial and temporal resolution, P describes the probability of infection of 1 centimeter roots within 1 day. So that is really important. We've now got some definitions in here. So if I write that down, P equals, I'm just going to write infection and then 1 centimeter, 1 day. Like that, and that was capital P. And it says the probability lowercase p that a root segment of length dx becomes infected over a time period of dt is then given by this. So this then brings in a couple of extra factors. That's already fully defined, so I'm not going to write a note down on that. Where 1 minus p is the probability of the 1 centimeter root not being infected within a day, which is, if you're familiar with kind of maths concepts, this is just the complementary event, so the leftovers of 1. If there's a 50% or if there's a 30% chance of infection within a day, then there's a 70% chance of it not being infected by default. And then it also says 1 minus p to the power of dt times dx is the probability of not being infected again over a period of dt with a root segment length of dx in centimeters, and time is measured in days. So then infection can occur everywhere but is more likely near the root apex. We assume a so-called susceptible phase of root development, i.e. that there is a maximum age until which the root can become infected. We also provide the possibility to set a minimum age for infection, but set it equal to 0 in all our simulations. Therefore, the actual probability, PA, of infection is given by. So this is now referred to as actual probability. So we're looking for those trigger words in the questions now. And we've also got a note. So whenever this happens, whenever you get given a note, always pay close attention. You'll pretty much always need to use it in somewhere in the maths. So then question 1, the approximate ratio of the weight of clay to zeolite in the boxes used in the first stage is closest to. Now I've basically put this in as a trick question. So of course, if you go to the table and you look to clay, you'll see 33%, right? And then the problem is you'll see zeolite and it's not there in the table, but it was there over here. Now, if we've got 10, 45, 45, it means that 45%, that third one, represents, they're all respective, and zeolite was the third item in the list. So that means that the 45% at the end there represents 45% zeolite. Now, the trick to that is going to be that if you just do 33 to 45, you get roughly 3 to 4 as a ratio like this. So then, and it's not actually shown in the options. So this kind of throws things off a little bit. So what we then have to do is look at the fact that it's not actually 33% in the boxes, it's 33% in the soil, but the soil only made up 10% of the actual mixture that was in the boxes. So we have to account for that as well. So what that means is that even though the clay is 33% of the soil, because that only makes up 10%, we need 10% of that, which brings us down to 3.3% in the final mixture that is actually clay. So if we do that now, that's 3.3% compared to, and then what was the percentage of the zeolite? That was 45%, like that. And so if we simplify this to basically around about 3 to 45%, then we can simplify that by dividing everything by 3, and we get 1 to 15. And the answer then is C. So always look out for proportions when they start talking about, this can be applied in chemistry when it comes to things like dilution factors and that kind of thing. Always look out for your percentages. So then question 2, if the likelihood of an AM infection of a 1 centimeter root within 1 day is 0.2, what's the probability that it's infected within 1 week? We immediately know that is DT is 7, because remember, time was measured in days. So that's what we're being asked for. But the first thing is it gives us a statement here. So the likelihood of an infection 1 centimeter within 1 day, if you remember, that was actually the definition of capital P. So we're actually being told here that capital P is 0.2, like that. what is the probability that is infected within 1 week? We will now use this formula. So P is equal to 1 take away 0.2 to the power of, now dt is 7, and the length of the root, it's still the 1 centimeter root that we're talking about, so we just put in 1, and we get 1 minus, this becomes 0.8 to the power of 7. Now this is where it gets a little bit tricky, because no, you're not expected to do very heavy maths in GAMSAT or anything, but what you can be expected to do is know how to convert between common decimals and their fractions. So I'm just going to zoom in here. We could write the 0.8 as 4/5 instead. I always go to fractions whenever I'm trying to do maths to it, because fractions are always easier because you're working with whole numbers instead rather than decimals. It's personal preference though. And then what we can do here is, this is where we start to trigger and we go, okay, well 4/5, we saw that in the notes, right? And that was given, I've lost it now. Here it is, I boxed it there. 4/5 to the power of 6 is approximately 0.25. So if we come back over here, I would work out how I can get 4/5 to the power of 6 in here. And if we reverse one of the index laws, we can split the power of 7 into 6 and 1. And that way then now we know that this is 0.25, and we're just timesing that by 4/5. And then we can actually start to work out this probability. So then 1 minus, and now what we can do is we can go, okay, so we can think of this as 1/4. It's probably the easiest, and we'll just jump up here. And then finally we get 1 minus, now top by top, bottom by bottom, so 4/20. And then we end up with 16/20, which becomes 4/5, which is actually 0.8 coincidentally. And then we've got our probability, like that. So whenever you're using numbers given in the notes, always try to find where they link in, and then basically make an excuse to make it fit in, even if it means like separating things just for the sake of getting that 4/5 to the power of 6 in there, so you can apply it, and that is often how you unlock the question. So then question 3, the probability that a 1 centimeter root is infected within 1 day is half as likely as it is not being infected, and the same likelihood that it is not infected within 10 days for a root length of what? Now, I've purposely written this one where if you got onto the trick of question 2, it makes it a little bit easier to see where it's going, but it is still very heavy in the reading and it's very easy to get overwhelmed. So we're going to break this down bit by bit. The first statement is the probability that a 1 centimeter root is infected within 1 day. That just means capital P. Then it says is, so is equal to half as likely as it not being infected. So that is this. Not being infected is 1 minus P. So if that is equal to half of this, we can now solve for capital P. It's just a maths equation now. So P is equal to, now we could probably just divide the half across and times the 2 up like that. And then from there we can add P across this way, and we get P is 1/3 like that. And therefore 1 minus P is 2/3, just in case we need it. So that's the first bit done. The next thing it says is that P, again, which was this, is the same likelihood. It's like a double-edged or double-pronged statement. It has the same likelihood that it is not infected within 10 days for a root length of. So not infected was not the whole equation for lowercase p, it was just 1 minus p to the power of dt times dx, like this. And it's saying that this is equal to it for 10 days. Now we know that capital P is 1/3. And then over here we can do 1 minus 1/3 or 2/3. Let's just save ourselves a bit of time there. Like this. And then dt was 10 days, and we're trying to work out the root stem length like that, dx. And it's effectively now a solve question, and we're going to see which of these matches up. So in this case, now we have to rearrange and solve. So rearranging this into a log, we get log of base 1/3 is equal to 10 dx. If you're a little bit unsure about your logs, check out, I'll link it below as well. I've made a logs and exponentials video that explains all the rearrangement, but I won't kill too much time on that here. Then the next thing is we don't really have a very good base here. So there's something called base switching. Now, I don't think that base switching in logs is actually very likely to ever be used in GAMSAT. I've never seen it myself, but it's a handy thing to know because it might actually make an otherwise complex process a little bit easier for yourself. So Here, I can see they both have 1/3, 2/3. So I'm going to target a base of 3. And the idea is that I just remember this. I just put a line like this, and I know that when I'm choosing a new base, I have to do the log with that base of this number over the log with that base of the number at the bottom, which is the old base. Like that becomes a fraction. So log 3 of 2/3, and that should still be equal to 10 times dx, like that. So now at this point then, I want to make them all expressed with the same base. So this would be 3 to the negative 1 for the 1/3. And this one over here would be the same as log 3 of 1/3 plus log 3 of 2, like this, is equal to 10 dx, like that. Because now we can start to separate things. Now from there, this is a bit of a chaotic kind of log question really, but let's just do it anyway. So then the next thing is we can bring this down the front. So we get negative 1 times log 3 of 3, which that is going to cancel anyway. The exact same thing happens here with this one. So I'll cut some corners there. We know that's going to be negative 1 times log 3 of 3, and then plus, and then here we have our log 3 of 2. And so from the notes as well, which I realize I didn't have in this one, but it'll already be up there, is we know that log 3 of 2 is 0.6. We're told that in the notes. So therefore, if we add that in, 0.6 is equal to 10 dx. And then we have negative 1 over, negative 1 plus 0.6 is negative 0.4, is equal to 10 dx. And then this here, the negatives cancel, and we can call this 10 over 4 is equal to 10 dx. The 10s can actually divide off or cancel, and we get 1/4 is dx, and so therefore the distance will be around about 0.25 of a centimetre. And so if we look, the only one that works is then B. Cool. Then question 4, so this one taking up the whole screen here, a graphs question. Which of the following best displays the actual probability of AM infection? So actual probability was the PA formula, like that, and let's just bring that back here. So that was this one here, 1 minus age on max age times P. Okay, so 1 minus age on max age multiplied by P. Now what we have to do here is, this is just a graphical analysis type question, understanding the basic shapes of graphs of simple equations. So first of all, we have to look at the axes. I'm just going to go with test and check here. I'm going to look at A. It says age is like my X variable, and I'm measuring PA. So if I look over here, that means that I'm assuming everything else is a constant. And so what that means is that then if I rewrite this, it's a whole lot easier if I just make up numbers for everything else. So this can become X over. I like not to use ones like this. It just allows me to see what kind of shape I'm actually dealing with. So if I expand that out, then I'll end up getting 2 take away X. And I can see that is just a linear function, and it has a negative gradient. So therefore the graph against age should be linear and it should be negative. So this one looks good, this one looks good, this one looks good, but this one is clearly wrong. So already I know that one's out. The next one I'm going to look at is the second graph, and that has maximum age as the x-axis. So if I go back to my equation, now I'm going to make this the x instead and see what I'm dealing with. So this time it's going to be PA is equal to 1 minus, so I'm going to put a number for age. I'm just going to put 2 over x multiplied by 2, and then we're going to get 2 minus 4 on x. I can see here definitely not linear, so that means this is out, this is out, and this is out. And so by default, I know the answer is A, because really you don't really need to know the shapes of every different mathematical function, but if you did want to know, this is a hyperbolic function, and they do have, at least part of their graph does have this curved shape like this, and this is the shape that it would take. That's it. So it's just a mathematical analysis question. You can see I'm not using any biology knowledge whatsoever. Cool. Then question 5, nitrogen in the soil can be utilized by the fungal root system and converted into nitrogen dioxide, which is then contributed to the atmosphere. If 1 kilogram of the mixture from the 90 boxes was tested after 1 week of fungal root growth and found that it contained 0.07 grams of nitrogen by mass. The theoretical yield rate of nitrogen dioxide gas, if 1 mole of gas occupies 24 litres in open air, is what? Now again, that last bit I've made that worded very, very confusedly, but let's just break this down. So first of all, we have a kilo or 1,000 grams of the soil mixture. Now what that means is, remember that 10% of that, of the mix, is the low P soil, which is in table 3, right? Now what we're looking for is nitrogen specifically. So if we go across to the table, I might zoom that out a little bit, we can see nitrogen makes up 0.13% of that particular mixture. But if you think about it, it's only 10% of our whole thing. We've effectively like diluted it, right? Because we've gone from being 10% to 100%. So that means that in terms of percentages, 0.13% diluted 10 times up to a factor of down to 1/10 of its value, because we made it 10%. So if we do that, so that actually means its actual contribution is 0.013% of nitrogen in the final mixture. If we then work out what that is as a mass at the beginning, that is before it's actually been reacted, from there that would be 0.00013 as a proportion, that percentage of 1,000 grams. And so if we do that, that's just timesing by 1,000. So we get there, so we get 0.13 grams of nitrogen. However, then after a week, because that was 7 days, after a week we have 0.07 grams. So that means 0.13 take away 0.07 means that we've lost 0.06 grams of nitrogen, like that. So then the next thing to do is to work out, right, well, how many litres of volume is this over the course of the 7 days? Okay, so I made a slight error in the original recording, so I'm just going to fix this up now. So you've got 0.06 grams of nitrogen that is being reacted, and then what you've got to do is work out the number of moles of nitrogen, and you can do that by just doing mass over molar mass. So therefore that would be 0.06, which we're going to put in scientific notation, 6 × 10⁻², divide that by the molar mass of nitrogen, which is 14. And then we can see here, this is basically 7/14, so this is where we're going to start estimating. So it's around about half times 10⁻², which is the same as 5 times 10⁻3. We can acknowledge that we're slightly underestimating, if anything, but it is still all in estimates. The next thing then is to look at the ratio of nitrogen from NO2 to N, and you can see it's a 1-to-1 in terms of the amount of nitrogen. There's 1 mole of nitrogen in every 1 mole of nitrogen dioxide. So that means that the number of moles of nitrogen dioxide produced would be exactly the same as the number of moles of nitrogen atoms, 5 × 10⁻3. Then finally, to get the volume, that then would be this number of moles multiplied by 24 litres per mole. And that then, again, if we estimate this, this would give us 72, if the pen wants to work with me, 72 × 10⁻3 litres, which is the same as around about 72 mils in that case. But remember that that was over the course of 7 days, and we're being asked for a yield rate. So if we do 72 divided by 7, we get approximately 10 mils per day, and then that leads us to our answer of D. So then with unit 2, now we have more like a physics type question. So we've got CT scans are produced by taking multiple X-ray images from multiple positions with the source and detector rotating around the object, taking multiple 2-dimensional slices, which can then be collated into a 3-dimensional computerized image. Images are dependent upon the absorption and scattering of the X-rays by the material, which is dependent on the attenuation coefficient, mu, of the material. Generally, the attenuation coefficient is proportional to the density of the object and the electron density of the material. So I'm going to write that down. That is proportional to density, which is directly proportional to electron density as well. Cool. So then we have a table of a bunch of different coefficients. I'm not going to fuss about those. Tissues can have an average attenuation value calculated in Hounsfield units, H, which are measured relative to the attenuation coefficient of water, given humans primarily consist of water. We have another formula. I wouldn't analyze it too closely. And then typically a CT scan has a range of 2000 H. However, most soft tissues only exist within a very small fraction of this, meaning that CT scans need to be particularly sensitive in order to produce clear images. Image quality and clarity is dependent on the Hounsfield units of the tissue, with larger Hounsfield units giving greater image resolution and therefore quality and clarity. So that's another mathematical relationship. So basically we've got increased H equals increased clarity or quality and resolution, all those different words. Which of the following would produce the clearest image? Okay, I might switch colors here because green might be a little bit hard to actually see. So which of the following would produce the clearest image? It's going to be the one that has the highest H value. So we're just going to look over here. Now remember, these are mu values and H is calculated using this formula here. So what I could do is, rather than, I could do test and check. What I could also do is look for a pattern, or I could mathematically analyze. H of the tissue is mu of the tissue minus mu of the water over mu of the water times 1,000. So if I split this, it's mu of tissue over mu water, I might just do W, minus mu water over mu water times 1,000, like that. And so now that actually means that we've got H is equal to mu tissue over mu water minus 1 times 1,000. That's another way to look at it. And so now what that means is that in terms of proportionality, the only thing that can actually vary is the mu of the tissue. And you can see that it is directly proportional because the mu of the water is going to be a constant, right? So I'm just going to call that a 1, take away 1 times 1,000, like that. And I can see now H is directly proportional to mu. So I don't really need to overthink this too much. The one that produces the highest image is the one that has the highest H value, which has the highest mu value. So that would be bone. And there's my answer. Cool. All right, I'm going to scribble some of that off just so we've got some room here because there's another maths question coming up. So then question 2, how much clearer is a CT image of muscle tendon than an image of muscle? Now, if we're measuring clarity in terms of the H values, how much clearer? This is a ratio, so we need to divide them. So we're doing the tendon over the muscle, right? Like this. So I might just zoom this in so I'm a little bit neater. Here we go. So we're trying to do H tendon over H muscle because H is directly proportional to image clarity. And we saw before, let's actually take that shortcut that we had mu, so this would be mu of tendon over mu of tendon minus, no, mu of tendon minus water, minus mu of water over mu water times 1,000, all divided by, and then it'd be mu of muscle minus mu water over mu water, can't even spell, times 1,000, and a couple of things will start to cancel off. So you can see the thousands will cancel, the mu water will also cancel, and it's really just a ratio of these two here, these two numerators. So if we start going over to our numbers, we've got water is 100, muscle is 180, and tendon is 190. So if we put those in, we then have 190 minus 100 divided by, and then this lot here, which was 180 minus 100, and we get 90 over 80, like that, which is 1.125, right? Now this is where knowing your fractions again is really helpful because we can make that 9/8, which is 1 and 1/8, and knowing that 1/8 is 0.125 or 12.5% is really helpful. So how much more clear is it? Not the whole 112, just the 12.5%. There we go. So therefore the closest is C. So then which of the following materials could not be appropriately imaged using a medical CT scanner? So with this one, it told us in here that it has a range of 2,000. So this is a bit tricky because we don't actually know what the lower and upper limits are. We just know that they are 2,000 H values apart, right? So what that then means is we need to look at, well, something's either below the lower limit or above the upper limit, right? Now, if we want to work that out, we can look at what is the lowest and the highest H values. So if we can image, for example, bone, that would have to have the highest H value. When we do that, 230 take away 100 on 100 times 1,000, like that. So we get 130 over 100 times 1,000, which gives us 1.3 times 1,000, or 1,300. So if this is our maximum, or even if this is our lower limit, right? Let's make this the lower limit, like that. On a scale, 1,300, we have a range of 2,000, right? So therefore, it can go up to 3,300, but it can't go beyond it. So basically, anything that has a H value above 3,300 theoretically should not be possible. If we can image bone, and let's say that bone is on the lower limit, then 3,300 is the highest that it could go, right? So then the next thing is, rather than actually testing each of these, we could then just check and see like what is the mu value that would give you 3,300. So if we let H equal 3,300, excuse my messy handwriting, then we can get the mu that we're looking for, minus 100 over 100 times 1,000. We can divide the 1,000, we get 3.3 is equal to mu minus 100 over 100. We can times the 100 across, get 330 is equal to mu minus 100. And now we know the maximum mu value that's possible is then going to be 430. So anything beyond that is not possible. And so immediately then iron must be the answer. Now these are just made up numbers. I have no idea what they actually are, but for the sake of the question. All right, and then question 4, individual attenuation coefficients of tissues are commonly magnified by a factor of 1,000 in order to amplify the small scale differences between the coefficients of each material. A graph of the Hounsfield value of materials against their magnified tissue attenuation coefficients would be best represented by. So another graphical interpretation question, right? We have to take the equations and then understand what its shape would look like. So if you remember, H was equal to mu, take away 100 over 100 times 1,000. So they're all suggesting they're linear. We're using mu as the x value. So if we expand this out, we can get this as mu on 100 minus 100 on 100, and then times 1,000. We can then expand that a little bit further. So this then is going to be mu on 100 minus 1 all times 1,000. This then gives us 1, I'm doing it in full, you can obviously cut corners wherever you're comfortable, but just for explanation's sake, minus 1,000. And then finally the 1,000 and the 100 can cancel off a little bit and you can get 10 mu minus 1,000. So it definitely is linear. And we can see that we have a y-intercept here, a vertical intercept of negative 1,000. So that means that B is good, A is good, and it has a gradient of 10. So what that means is we have to check what our x-intercepts are. You could just solve the x-intercept and match it. This one says it has a gradient of 1, which is not right. It should have a gradient of 10. This would have a gradient of 10. We can do that. We can do rise over run like this. You can see it's got a rise of 1,000, a run of 100. So 1,000 over 100 gives you a ratio of 10. So we know then that the answer has to be A in that case. And there we go. Cool. All right. Hopefully that was helpful. That's 9 more questions in the bank. Hopefully the practice is going well. If you're starting preparing for September now, or if you're preparing for another sitting or anything like that, then good luck. And I'll just keep banging these questions out. But hopefully some of the maths focused stuff from this one was really useful. You can see that you're not always going to be applying like traditional biology, chemistry, and physics in questions. A lot of it now is about like, well, it hasn't really even changed that much, but definitely a really valuable skill is being able to process mathematical information and make mathematical assumptions confidently. It's not necessarily testing your knowledge of maths concepts. You're not going to be asked like what's the quadratic formula or anything like that. It's generally just skills about ratios, percentages, graphical interpretations, that kind of thing. But anyway, I'll stop rambling. Hopefully that's enough. Hopefully that was helpful, and I will see you guys in the next one.